Okay, so I'm recording now. Welcome back to your second class this week. We started yesterday chapter or unit number 5, which is our second last unit. It's a larger unit, chapter 6 being one of the smallest units, but it's a pretty useful unit, and it's a pretty easy unit in the sense that it's just a lot of kind of terms and information. There's no calculations or naming or anything like that. So the other day we talked about distillation and how important it is for petrochemical processes. And this is a slide that I'm like, this is obviously kind of like a very cartoony type image. This is an image I used years and years ago when I first came here. I was actually working with the engineering faculty teaching, I think it was 2420, or no, 2430. So some of you guys might have done a course called CH2420, where I showed this image. I'm actually not going to focus much on this image because later in my notes, if you'll let me skip further ahead just for 1 second, on slide 47, we will look more into this fractional distillation concept in greater detail. You can tell that this image is a lot less kind of cartoony and has a lot more information for us. So I'll kind of come back to the topic in this slide, in slide 47. But the purpose of this slide is kind of to illustrate a couple of things we'll talk about today. So you would have like a feed tube going in here to the bottom of your fractional distillation column. The feed tube obviously feeds into the column, the crude oil, or crude petroleum, to be processed, to be, I was almost going to say filtered, I should say to be separated. But distillation is not the same as filtration. Distillation is separating these things based on their boiling points. After they're separated, so once they've been heated up and separated into their components, there's another process that typically happens. And that process can be reforming, alkylation, and cracking. And these processes we are going to look at today, okay? And, chapter 5, it'll be a lot of me talking. There's really no practice problems. There's no, things I can get you to try on your own. It's just a lot of theory. So you'll kind of have to, just kind of follow along with me for the next week or so while we work through chapter 5. Okay, so like I said, feed tube here, feedstock, you might call it, brings the crude oil into the fractional distillation unit. Once it's separated based on the boiling point property, there's other processes that happen for refining. The first process is one you might have learned about in chemistry 1120, and it's called cracking. And this is one of my favorite processes because the name is exactly what it sounds like. What I mean is, cracking in English means breaking something into smaller pieces, right? If you crack an object, the term again in English means to break something. And if you you crack a pencil or you crack a piece of glass, it will turn into smaller objects. So in petrochemistry, cracking is the process where a large complex organic molecule, and really all you need to think about is long chain hydrocarbons, are broken into simpler molecules like lighter, smaller chain hydrocarbons. In simple words, hydrocarbon cracking, and this is kind of the definition that you guys would really need to consider, is cracking is the process of breaking a large hydrocarbon into a smaller one, or into smaller ones, plural. So if I had a long carbon chain and I cracked it down in the middle, we would have two hydrocarbons from that process, two smaller ones. The process itself is pretty easy. If you increase the pressure and temperature to a very large amount, typically high chain or high carbon hydrocarbons will crack and break into smaller products. The products that you get from cracking depend on the temperature you use and if you have a catalyst or not. Now, let me just check the chat here. Yeah, so like Niam mentions, crack means break partially, not break completely. I mean, cracking it's a complete break in the hydrocarbon sense. You don't it's not like breaking a double bond into a single one or a triple into a double. It is literally cracking a hydrocarbon chain into two smaller pieces. You break the chain. One thing I'll mention, let me just clear my writing here. And we did this at the end of chapter 3, is remember what a catalyst is. This is something that helps a chemical reaction without being used. Or, well, being used is the wrong word, without being consumed. So it helps a reaction along, but it doesn't, get consumed up by that particular reaction. And I don't know if you guys can remember Chemistry 1121 as well as I can, because I've taught it 100 million times. But really a good way to think about a catalyst is it's a shortcut in a chemical reaction. It provides a shortcut or an alternate energy pathway. So in simple words, it can help a reaction happen using less energy, or sorry, I should say, making it more energetically favorable. So catalysts are using cracking to help the reaction along. And as Niam says, like the literal definition from Chemistry 1121, as Niam says, is it increases the reaction rate. Yeah, I mean, it helps the reaction happen by lowering the activation energy, the energy it takes to get that reaction to actually happen. Now, when I was doing research for this course, like the petrochemical industry is so diverse, so complex. It's been in development for the last 100 or maybe 120, 130 years or so. There's lots of different forms of cracking. So rather than look at outdated forms or lots of different types of cracking, I decided to focus on one of the most important conversion processes and commonly used processes called fluid catalytic cracking. It's widely used, meaning used all over the world, to convert high molecular weight hydrocarbons into something a little bit more valuable. And there's a theme in these processes. The theme is we need to make the product that will make us the most money, right? So when you look at the oil and gas industry all over the world, this is an industry that is so important to local economy, or maybe not local, but like a country's GDP, gross domestic product. So Qatar, for example, huge economy based around oil and gas, very much like where I'm from. And when you're breaking these products down, you need to consider, what do consumers need? How can we make money? So fluid catalytic cracking is used often because it takes these hydrocarbon, high molecular weight hydrocarbons, and breaks them into something that is valuable, like gasoline. Now, um, when I like, okay, I'm gonna make myself sound old now, but like I'd say 15, maybe 18 years ago, um, I can honestly remember being in a chemistry course, learning about cracking and talking about thermal cracking. So this was, when I was learning chemistry, I think the book I used was in like from the 1980s. And thermal cracking is something you might have heard in other courses. You can find information online. This was kind of the more commonly used type of cracking, and it's exactly what it sounds like. Thermal cracking would just involve high heat, typically high pressure, but it's almost been replaced, almost completely replaced, sorry, by catalytic cracking because it produces, so catalytic cracking produces more gasoline and a better product. If you weren't here yesterday, we talked about octane rating. This is kind of like the quality of your product, in particular, the quality of this octane or fuel source. I mentioned yesterday when you guys go to get gas, there's different types. There's silver and gold. That's your octane rating. And gold costs more money because it has a higher rating. So again, like think about it. If you're making a product, you work at a restaurant and you make sandwiches. If you can make more sandwiches that are higher quality, you can sell them for more money. So catalytic cracking is preferred over something old like thermal cracking because you can get more gasoline, so more product. In chemistry, we would call this a higher yield. I don't know if you remember that term from Chemistry 1120, and you get a better rating. Another reason you would use catalytic cracking is it produces byproducts that have more double bonds. Carbon-carbon double bonds in the industry, oil and gas, they call them olefins. You might have heard of that in another course. In chemistry, we would call them alkenes. In the oil and gas industry, they might call them olefins. These have double bonds. Double bonded formulas are also very good for making money because you can use double bonds for reactions. So things like polymers, right? Remember, a double bond is a perfect site for an addition reaction in chemistry, meaning we can turn that double bond into like an alcohol, a ketone, a carboxylic acid. You can take that double bond and dehydrate it, meaning kind of remove the double bond and bond it to something else, making a polymer. So, I mean, really the idea here is, if I asked you why is catalytic cracking used today over something like thermal cracking, it's all about the money. You get better product, more useful product than thermal cracking. So again, all about the money. All right. I'm sorry, I'm just reading the chat. Naim, it's kind of the same thing. So if you're not in the chat, or you can't see the chat, the question was, is it because of the high yield or is it because of the money, or is it's more economical? Like that's kind of an open question because let me answer it in two ways. When you say something in English, if something is more economic, now this is my understanding. When you say if something is more economical, you can also mean that it's cheaper to do. So not only does it make more money, it's a cheaper process. And catalytic cracking, because it uses a catalyst to help the reaction, it probably over time would save you money. But really what I was talking about on the other slide is because you can get more product from catalytic cracking, you can sell more, right? Remember, I mentioned like the sandwich shop. If you worked at a restaurant making sandwiches and you found out a way to make 100 sandwiches in an hour instead of 50 sandwiches, you're going to sell more, you're going to make more money. So if catalytic cracking can produce more gasoline, that is even better. You will also make more money. So that's kind of what I meant by talking about the economics of cracking. More product, more money. Could be like a rap song somewhere. So about catalytic cracking, you guys have to remember this diagram perfectly. Obviously, I'm kidding. You do not need to memorize this diagram perfectly. This is not one of your other engineering courses where we'll be doing or looking at flow diagrams or anything like that. You do not need to memorize this at all. This is just an example of a catalytic cracking system, and it really shows how modern technology has really improved this process. There's so much going on in a modern fluid catalytic cracking process. You can see the distillation column where it fits into that process. And again, this is not something you need to memorize or know for this course. Don't worry. I didn't mean to scare you guys. Again, this is a chemistry course, right? Not like a chemical process course or an engineering, course. Really, I'm concerned with the chemistry of it. What happens to the molecules, not, what the technology is to do that. So don't worry about this graph. Okay. I kind of thought I had a picture, but I guess I don't. Or not a picture, but just like a chemical example. And really, the chemical example here is if you took a long carbon chain and you added to that heat and a catalyst, you would get smaller chains. That's really it. And this isn't a real chemical formula, guys. I'm not counting carbons. I'm not worried about anything. I'm just saying if you take a very long hydrocarbon chain and you add heat and a catalyst, it can break it down into 2 smaller hydrocarbons, or 3 or 4 smaller hydrocarbons. So you don't have to write reactions like this in this course, don't worry. But I mean, if I asked you, what type of reaction do you think this would be? It's definitely cracking. Okay, so this kind of sneaks in here. This is part of this concept of octane number. I introduced octane number in the first section. There are several ways to evaluate or look at the octane number of a fuel source. And there's 2 methods I'm going to look at, just 2 methods I'm going to look at today, the RON and the MON. So the RON is a worldwide rating, and again, I mentioned in the class yesterday, embarrassingly, I don't drive here. I usually take public transit or Uber or something like that. But I certainly drive back home, back in Canada. I miss my little car back home. And when I go to get gas, you can see typically which system of octane rating they are using on the pump. And sorry, when I say gas, I mean petrol. Typically, the worldwide rating or way to calculate the quality of your gas or petrol is the RON. How do they test fuel efficiency? How do they test the octane number or rating of a petroleum product? Well, they run it basically in a test engine. Okay, so RON, the octane number that is used most places in the world, is determined by running that fuel into a test engine. It has controlled conditions, so repeatable conditions, and they compare the results with other gases or other mixtures of gases, typically isooctane and heptane. Now, what do you need to know from this slide? if I asked you guys, how does someone determine octane number? They run the fuel in a test engine under controlled conditions. I mean, that's how most things in science are evaluated. If I want to test something, I use it, or we would say run it under controlled conditions. It could be standard pressure, temperature, volume, all sorts of things. So it kind of follows the scientific method here. If I want to figure out the quality of a gasoline or a petrol in a engine, I would run it then in a test engine, but make sure it was under controlled conditions so I could repeat that test. That's what science is all about. Completely repeatable. In the chat there, I did say silver and gold. Those are octane ratings in Qatar. And where I'm from, there's like standard, premium, and then superior or something. If you get gas where I'm from, sorry, I keep saying gas. If you get petrol where I'm from, first of all, if you go to Canada, don't ask for petrol, ask for gas. If you guys watch American movies, they always say, oh, we ran out of gas, or we need to get more gas. They're talking about petrol. But if you ever came to visit me and you needed to get some petrol for your vehicle, and you went to we call it a gas station or petrol station, my version of a Wakood, they would ask you if you want it. Well, first you have to pump your own gas. So you'd have to get out of your car and do it yourself. And you would have to personally select one of 3 options. But here, I think there's silver and gold. There might be more. I don't know. I don't drive. I think the only time in this country I've been into a gas station or a petrol station to get petrol is I had an Uber driver one time pick me up from work, or maybe I was going to work, I can't remember. And the Uber driver picked me up and his car was on empty, like literally the light was on, no gas. And he said, do you mind if I get gas? And I try to be polite, but I'm late for work or something. I'm like, maybe you should have picked up gas before you accepted my Uber call. But anyways, that was it. I was probably late for work that day. Anyways, sorry, little tangent. Another type of octane rating, and you guys don't need to memorize either type. Really what I mentioned is what you need to know. Octane number is determined by running the test subject, or in this case, the octane, in a test engine under controlled conditions. Other countries use a different type of rating called MON, motor octane number. And the big difference here is the RPMs, the speed of rotations in that engine. So in most countries in Europe, Australia, New Zealand, they use the RON, and they probably use that in the Middle East as well. But I know where I'm from, or the USA, they would use something else, even more complicated, but they call it the anti-knock index, the AKI. So what does that mean? What is this anti-knock index business? Well, anti-knocking is kind of like a term people would use in describing an engine. So knocking is related to the ignition of the combustion of the air-fuel mixture in your engine. And remember, when an octane number is high, you have a high quality gas, the ignition happens at a later phase due to the compression of the gas. So anti-knock index is a measurement of the combustion of that gas and related to octane number. And you don't have to know that either. All you truly need to know is that if I ask you, wink, 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 how is octane number evaluated? It's evaluated by running the fuel in a test engine under controlled conditions. All right, cool. So, okay, that was cracking. And I know this kind of snuck in here, but I'm just following your course outline. So we've looked at cracking. And again, cracking is useful because you get a more gasoline with a higher octane rating. I explained what octane rating is, and I'm going to look at 2 more processes today, and then we'll take a break. You are expected to know 4 of these processes in some way. You don't have to memorize them perfectly or anything like that, but you should know cracking, alkylation, isomerization, or platforming in some shape or form. Like in an old exam that I typically give, I would get people to explain like 2 out of 3 of these, or 2 out of 4 of these. So, okay, what's another chemical process or a refining process after we've separated the crude oil? Alkylation is another. Alkylation is named because it's the transfer of an alkyl group, so a small carbon chain from one molecule to another. So like that's the chemistry definition. When you're talking about oil refining, typically isobutane, which I'll show you on the next slide or the one after that, excuse me, is alkylated with low molecular weight alkenes with an acid catalyst. Now, you don't need to memorize that at all, but the idea is typically in oil refining, you would take isobutane and alkylate that, or transfer an alkyl group with a low weight alkene. Now remember, the alkene has a double bond, and that makes it reactive. So we can take low weight alkenes like propene or butene. These are, the smallest alkenes you can get, or some of the smallest alkenes. And we're going to add that to isobutane. So I think I have a picture right here. So the product of alkylation in the oil refining context is called the alkylate, and it's composed of a mixture of highly octaned branched hydrocarbons. So here's an example on the bottom of alkylation. And I wish I was in front of you to show you this. I guess I could probably, let me draw it first and then I might find a way to show you. But here I have my isobutane. Isobutane is a name for, also you could call it well, you don't even need the number there, but I'll keep the number, 2-methylpropane. This is traditionally called isobutane. And I'm reacting it with propene in this case. And what happens is this has a double bond. One of the double bonds opens up and didn't mean to do that. One of the double bonds opens up and joins here to this chain, and then we get a longer carbon chain. That's it, that's alkylation. All right, now, the way that I typically explain this in class is, I kind of actually talked about this before. Let me just start my video here. Okay, so you guys can kind of see me. Maybe you can see me on the screen there if you have that part of the Zoom chat open. The idea is, I'll kind of back up a little bit, is we have this like kind of molecule here, like single molecule. And then we have a double bond, an alkene. And like you can think of bonding like holding hands. So again, if you can see my video in the Zoom window, imagine a double bond like somebody doing this, and also imagine bonds like objects holding hands. So what happens is that double bond kind of opens up and then grabs onto another hydrocarbon. So when I draw on the bottom that picture of the double bonds, like for example, like opening to grab the other hydrocarbon, I can't get my camera right because it's reversed. That's kind of what's happening. The double bond is breaking and adding itself to another chain, and we call that process alkylation. So alkylation results in a premium gasoline blending stock because of its anti-knock properties, or basically its high octane rating. When I say anti-knock properties, it's related to the combustion, which is the octane rating. So again, guys, the theme here, why are we doing this? Why are we taking a refined or separated hydrocarbon and then doing more things to it? Well, by cracking or by alkylation, you can get better, cleaner burning fuel. And that's how you make money. Um, if a industry or a petroleum, like a refinery, uses processes like catalytic cracking, polymerization, or alkylation from the crude oil, they can get a chemical yield of really exceptional gasoline at up to 70%. Unfortunately, there's always waste in this industry. In any industry, there's always waste, but it's getting better all the time. So using methods like cracking and alkylation, you can take some of the products of your refining, or I guess distillation, I guess I should say, and get a pretty decent yield of high quality gasoline. All right, I'm almost done. Let me just kind of go through isomerization, and that'll be it for me today. That'll be a good place to finish. It would have been nice to get through up to 5.10, but that's all. That's it. That's all we can do. Okay, one more. And this is a quick one. Now, in chemistry, not petroleum chemistry, but straight up chemistry, isomerization is defined as the process where one molecule is transformed into another, but it's just an isomer. So if you remember back in chapter 1, an isomer is, or isomers are different chemical structures, but they have the same molecular formula. And I mean, we've done this back in chapter 1. So like an isomer of, this is butane, would be, 2-methyl or methylpropane. So these are isomers. So another chemical process you can do in refining the petrochemical process is taking a carbon chain. You're not going to add anything to it. You're not going to crack it into 2 smaller molecules. You're simply going to rearrange the molecules to form an isomer. The isomerization process here it's gaining importance. So again, I did my research for this course within the last couple of years, and the isomerization process, that's hard to say, is gaining importance. You're seeing it more and more due to certain limitations of the products that we get. Again, the whole idea is like we refine the crude oil into its components, but then we want to change those components, and isomerization is another way to do that. By rearranging some molecules, you can upgrade their octane number. So you can take a hydrocarbon and rearrange it into a form that it has a higher octane rating when burned in those test engines. One of the ways that isomerization works is it can reduce benzene content and upgrade, which means improve, light fractions. And the word, I haven't mentioned this word yet, we'll talk about this word later, but naphtha fractions in the oil and gas industry are small molecules around 5 to 6 hydrocarbons. This is not a term that you would learn in a chemistry course. Naphtha is a specific term to the oil and gas industry that typically represents like pentane or pentane derivatives, hexane derivatives. So isomerization can improve the octane number of smaller fractions and increase the quality by reducing things like benzenes, basically purifying that product. Sorry, I just read the chat. Thank you, Naim. I kind of wish we had chemistry a little more. In chemistry 1120, we have it 4 times a week, which is a little bit easier because we get a lot more information covered. Um, Honestly, guys, it is 10:16, and I can't see myself finishing these 3 slides in the next couple of minutes. And you guys might have another class. I know I have another class at 11:30, or sorry, at 10:30. So I think I'm going to stop here. This was a good introduction to isomerization. I'm going to stop here, and we'll kind of finish this concept tomorrow for our last class this week. So tomorrow, I'd like to get into section 5.10. This is a really important section, so you should definitely come to class tomorrow. I'll kind of get into this because here in section 5.10, we're going to learn maybe one of the most important slides in chapter 5. But let's save that for tomorrow. It's 10:16, 10:17. I think we're good for today. So guys, I'm going to hit stop record. Saif, the lecture from Monday's class will be up today. I'll actually work on that now in the next 10 minutes to get that up for you if you want to watch class number 1 today. So that's it for me. I'll hit stop record. If you have any questions, let me know. And if not, have a wonderful day, and I'll see you tomorrow.